Let's see how we can find multiple optimal solutions that maximize the profit of the company Optimal Humus when using Python. Recall the model in standard form for the humus problem. The boundary lines of the feasible region are given by the constraints of the mathematical model. The corner points of the feasible region are the basic feasible solutions, of which one or more are optimal. For each of the 4 basic feasible solutions, 2 of the 4 variables are non-basic, which means that they are equal to 0. The optimal solution can be found by moving the objective function line in a perpendicular direction until moving it further would mean that the line leaves the feasible region. Now we have found the optimal solution with x1 equal to 72, x2 equal to 24, and both s1 and s2 equal to 0. The objective function value for this solution equals 540. When we change the coefficient of x1 in the objective function to 7.5, the slope of the objective function in the graph changes, which in this case increases the objective function value. The optimal solution stays the same, but the objective function value becomes 720. When moving along the objective function line, we end up in another optimal basic feasible solution. The objective function value stays the same, but the optimal solution changes to x1 equal to 96, x2 equal to 0, s1 equal to 48, and s2 equal to 0. We have already seen how to recognize multiple optimal solutions in the simplex tableau. If we use the simplex tableau to optimize the humus problem with the changed objective function, the final tableau will look like this, with optimal solution x1 equal to 72, x2 equal to 24, and both s1 and s2 equal to 0, and an objective function value of 720. Since the coefficient of non-basic variable s1 is 0 in the z-row, we know that there exist multiple optimal solutions. If we now let s1 be the entering basic variable, x2 will be the leaving basic variable. If we perform one additional iteration of the simplex method, we will end up with the following tableau giving us another optimal basic feasible solution, with x1 equal to 96, x2 equal to 0, s1 equal to 48, and s2 equal to 0. Note that the objective function value has not changed. We can also use Python to find another optimal basic feasible solution. If you run the Python file humuscbc, the value and reduced cost of both the decision and slack variables is given. The value represents the value of the decision and slack variables. In the final simplex tableau, the values of the basic variables are given in the right-hand side column, while the value of the non-basic variables, in this case both slack variables, is 0. The reduced cost of the decision and slack variables represent the cost of increasing the corresponding variable with 1 unit, which will reduce the value of the objective function. In the final simplex tableau, the reduced costs are given by the coefficients of both the decision and slack variables in the z-row of the final simplex tableau. When both the value and reduced cost of a decision or slack variable are 0, this indicates that there are multiple optimal solutions. For the humus problem, this is the case for the value and reduced cost of the slack variable of the first constraint, which means that we can increase the value of s1 without any costs, which will lead to another solution with the same objective function value. To find another optimal solution using Python, we need to make some modifications to the model. We start with the model in standard form. To find another optimal solution, we need to keep the original constraints. The other optimal solution that we want to find will have the same objective function value. This is added as a constraint. Recall from the simplex method that we can increase slack variable s1 without any cost. To find the next optimal basic feasible solution, we want to increase s1 as much as possible. This is modeled with the objective function. In our Python implementation, we have not modeled the slack variables explicitly. So we will rewrite the model to eliminate the need for the slack variables. To eliminate the slack variable from the objective function, we can rewrite S1 to 240 minus 2 times x1 minus 4 times x2 using the first constraint. The equality constraints can be transformed back to inequality constraints, and we keep the constraint on the objective function value. The slack variables are now eliminated from the objective function and constraints, so they can also be eliminated from the non-negativity constraints. If you implement this new model in Python, you will find another optimal solution with a profit of 720 euros, for which 96 kilograms of plain hummus is produced and 0 kilograms of beetroot hummus.